Testing, testing. Testing. Hello everyone, Marin Maths here. Now I'm going to do Physics 111 Common Exam review for the third Common Exam. I wish you the best of luck. Now for question 1, we have a glider of A of mass 2.5 kilograms moves with a speed 1.7 meters per second on a horizontal rail without friction. It collides elastically with glider B of identical mass 2.5 kilograms, which is initially at rest. Okay, after the collision, what is the value of the speed of glider A? Okay, in meters per second. Now we have to take advantage of two important things. First, because it is an elastic, okay, it is a elastic collision, we know energy is conserved. And so if energy is conserved, right, momentum is conserved, meaning that the sum of the forces of the system equals to 0, right? And we know that the initial energy equals to the final energy. So those are two important things to keep in mind when we solve momentum problems, right? Because over here we're going to have to use both of these facts. We're going to have to take advantage of the fact that the sum of forces is 0 and that energy is conserved. So first we're going to use momentum, conservation of momentum, which accounts for the fact that the forces, okay, cancel out, or there's no net force, right? So we know that initial momentum P0 equals to final momentum P final. Okay, so we have two gliders, right? We have a glider A that moves at an initial speed, and then it collides with a glider, okay, B, which is at a speed of 0, right? So it is at rest. Now, both of them have identical masses. Now, if you've ever seen a Newton's cradle, okay, at work, you'll find out that when this first ball hits, okay, the ball at rest, they'll basically switch velocities, okay? And that's exactly what's happening here. But I'll show you why that happens. So let's do conservation of momentum, and let's also take advantage of the fact that because energy is conserved, we know that the velocity initial of A minus the velocity initial of B equals to the negative of the velocity final of A, BA prime, minus VB prime. Okay, this is thanks to the conservation of energy, right? Given that this is a elastic collision. Now, if we use the conservation of momentum, we know that, okay, mVA plus mVV equals to mVA prime plus mVV prime. Oh, and let's also label the masses. This is mass A, this is mass B, this is mass A, and this is mass B. Okay, now we know that the initial velocity for B, right, for the glider B is 0, so we don't have to account for that term. Now, once we have these two equations, what we want to do is find VA prime, right? We want to find the speed of glider A. But if you take a look at the second equation, right, the one with mass, the momentum equation, we have VA, right, which is known. We have VA prime, which is the one we want to find, right? We want to find VA prime, but we don't have VB prime. So we have to use the first equation to solve for VB prime. Now, if we do that, we're going to end up with this. VB prime equals to VA plus VA prime. We substitute that into the momentum equation, and we get, okay, we get that MAVA prime equals to, okay, MAVA, and then minus minus VA, okay, and then, oh, well, there's a VA prime on this side. So it will be 2 times MA VA, okay. Now we divide by 2 times MA VA, okay. So if we do that, we're going to end up with the following. So, oh, my apologies. I think I forgot to multiply by the mass. Let's just do that again. Okay, so we have that. Once we substitute that in there, yeah, we have to distribute the mass of B. So it's going to be something like this. It's just I'm running out of space, so it's kind of annoying. Okay, so MA VA equals to MA VA prime, right? And then plus MV times, okay, our VB prime equation, which is going to be VA plus VA prime. Okay, so once we distribute MV, right, once we distribute the mass, we can factor out VA prime, right? And then we have something like MA plus MV times VA prime. And then we're going to have plus MB times VA, right? We can subtract that and then bring it to the other side. And we can factor out VA. So VA and then times MA minus, okay, MV. And here is the striking fact, right? This is the reason for why the velocity is 0. And you will see why. So the final equation for that will be, right, VA prime equals to VA and then times MA minus MB, all of that divided by MA plus MB. Now, we know that both masses are identical. So MA minus MB is just 0. So that is why, okay, the velocities switch. They basically switch velocities. Okay, so now for question 2, we have a glider. Okay, we have a glider of mass 0.5 kilograms, which hits the end of a horizontal rail. Right, so we have something like this. We have a sort of like a rail, right? This is what they call a rail, and then we have a glider. And then it hits, okay, the end of this rail. And then, okay, it bounces off with the same speed. So this is V 0, right? And then V final will be the negative of that, negative V. Okay. The collision is elastic, so energy is conserved, and takes place in an interval of 0.2 seconds with an average force of 100 newtons. What is the speed in meters per second of the glider? Okay, so we know from Newton's second law that the force, right, the net force equals to mass times acceleration. But now we're talking about average force. Now average force, okay, so F bar equals to mass times average velocity. And we know that average velocity is changing velocity, average acceleration is changing velocity over change in time. So if we substitute that into our equation, we get that F bar equals to m times change in velocity over change in time, and so we get the impulse equation. So we know that the average force times time, okay, equals to m delta v. And we're trying to look for the speed of the glider, right? We're trying to look for the speed in meters per second. Now, we know that F bar, right, equals to 100 newtons. The interval of time is going to be 0.2 or 1/5, okay, seconds. And then we know that the mass, okay, is 5 kilograms. So we can already, okay, kind of solve for this, but don't forget that the change in velocity, okay, will be basically 2 times as much as the original velocity, right? Because it bounces off with the same velocity, since it is a collision that is elastic. So we have twice the velocity. The change in velocity is twice the velocity, right? We're looking for the magnitude. Since we're looking for the speed, right? If they were asking for the velocity, then we know it would be negative, because v0, okay, so we have to write this out. Let's write delta v equals to f bar, okay, times the, I'm sorry, no, no, yeah, we're dividing by mass. So f bar times delta t divided by the mass. Okay, and we know that the change in velocity, so v final is v final minus v0. V final is negative v, and then minus v0, which is v, so it's negative 2v equals to f delta t over m. So we know that negative 2v equals to f delta t over m. So the velocity, right, or if we're looking for the speed, right, speed s is just going to be the magnitude of that, so the absolute value of that expression. So it's going to be f bar, right, times delta t divided by 2m. If you substitute the values, then you're going to get c. A man fell out of an airplane and barely survived. Okay, well, interesting happening. He was moving at a speed of 100 meters per second just before landing in deep snow on a mountainside. Experts estimated that the average force, right, the average net force, so F bar, on him was 600 newtons. And then we know that the velocity was, okay, the velocity is 100 meters per second. Now, he plowed the snow, okay, through the snow for 10 seconds. So that means that the interval of time is 10 seconds. And we're looking for the mass. Okay, so we know the equation already, right, for average force is going to be m delta v divided by delta t. But we're looking for, in this case, we're looking for the mass. So the mass will be equal to f bar times delta t divided by velocity. That's going to give us 600, right, times 10, and then divided by 100. The zeros cancel out, and we get that 6 times 10 is 60. So 60 kilograms. For question 4, a skier starts from rest and slides down from a high hill, and then, without losing energy, so energy is conserved, up a smaller hill. His speed is 10 meters per second at the top of the smaller hill. Ignore friction. What was the difference in height of the two hills in meters? Now over here, we have to, okay, take advantage of the fact that energy is conserved, meaning we can use the law of conservation of energy. Now, they tell us that the skier starts at rest and slides down from a high hill. So let's draw it. We have a high hill, and it comes down, and then it goes up to a smaller hill, right? Now here is the skier, and then we know that the initial velocity, right, is going to be 0, right? It's going to start from rest. So v0 is 0. And we know that the velocity at the top of the smaller hill, right, or right over here, is going to be 10 meters per second. Okay. They ask, what was the difference in height of the two hills? So here we have to assign, okay, some variables. So suppose the height of the highest hill is big H, and the height of the smaller hill is little h, okay? Just to assign some values. We're looking for the difference in height, so big H minus little h, okay? We're looking for that. Now, let's use the law of conservation of energy. We know that we have an initial energy, right? Which is potential energy, right? Right over here. Okay, at the top of the the highest hill, we have potential energy, specifically gravitational potential energy, but we don't have kinetic energy because the initial velocity is 0. So we say UG, right, gravitational potential energy, equals to the final energy. So if we're thinking about stopping at the top of this smaller hill, we know we have two types of energy. We're moving, and we also have, okay, a potential energy. So we have kinetic and potential. So kinetic energy, final, and then plus gravitational potential energy, final. All right. Now we can substitute these values. We know that the initial energy is mg times big H. Okay. And we know that the kinetic energy is basically 1/2 mass times velocity squared. And the final energy is going to be mg little h. Look at that. All the masses cancel out. We divide by mass on all sides. And we're trying to look for h minus h, right? Big H minus little h. We have gh over here, and we have g little h over here. So let's subtract g little h on both sides. So we're going to get something like this on this side. So we have big H minus little h, which is what we're looking for, times g. I factor out a g. All of that's equal to 1/2 v squared. So the difference in height essentially is going to be v squared over 2 times g, which in this case is at 10 squared, which is 100, divided by 2 times 9.8. If you think about it, 9.8 is pretty close to 10. So if you use that approximation, which is not, recommendable to do, it's just not right? But I mean, for the purposes of this test, you can approximate, okay, g as 10, and you're gonna get something like this: 100 over 2 times 10. Okay, look at that. Well, I mean, 1 0 cancels out, and then you get 5 meters per second, which is pretty darn close to 5.1. Okay, so D is the answer. So you don't have to oh my God, I don't know what's 100 divided by 2 times 9.8, and then plug it in the calculator and waste like 10 seconds just to do that. So just approximate the value if you can, right? It's not recommendable, however, to approximate values when they are in a function that is, okay, proportional to the square of some variable, right? If you're approximating, so that's going to come up on the next problem, I think. Let's see. A block slides with no friction and hits a spring with spring constant K equals to 200 newtons per meter. The block compresses the spring in a straight line, okay, for a distance of 0.15 meters. So we know that it's going to, this block is going to come over here and it's going to compress it for 0.15 meters. Okay, good. The block's kinetic energy in joules at that point is 0. So at the point when the block has completely stretched the spring to 0.15 meters, the kinetic energy of the block will be 0. And it makes sense, right? Because that's all it's going to compress the spring. That's the point when it will stop. So if it stops, the velocity is 0, and therefore the kinetic energy is 0. What was the initial kinetic energy in joules? Okay, so we're going to use conservation of energy, right? The law of conservation of energy. And we know that there are two types of energy in here, okay? One of them is, of course, right, if something's moving, the one thing you have to think about immediately is, well, kinetic energy, right? And the other one is, well, has to do with the force of a spring, right? The restoring force, to be more specific, of a spring. We know that the restoring force of a spring, according to Hooke's law, is Kx. Okay, so F restoring equals Kx. And if we want to find, okay, the work done by this restoring force, so essentially, okay, the change in energy by a spring, whether it's compressed, okay, by some distance, delta x, then, okay, we can say that F, okay, the work done, right, the work done by F is equal to the integral of the force, restoring force, times dx. Hey, what's up? From one point to another, so from x0 to x final. All right. So we have that's going to be the integral from x0 to x final, supposing that x0 is 0, right? We're going to assume x0 is 0, and x final is some value of k times x, right, dx. And we know the value for that integral, that's a trivial integral. We have that's going to be k times x squared divided by 2, right? X final squared. And then that's going to be the definition, right, for elastic potential energy. So that's going to be potential energy of a spring. That's going to be the potential energy of a spring, US. Okay. Now, we know that the initial energy for this system over here, okay, is kinetic energy. So kinetic energy initial, and there's no other energy. So the final energy, so that's initial energy, is equal to the final energy, in which case is going to be, okay, the potential energy, U sub S. So we're looking for the kinetic energy initial. So just kinetic energy initial is equal to 1/2 k times x squared. And we know that, okay, the distance that this block compresses the spring is 0.15 meters. And this is where okay, I come back to the last problem, that it's not good to approximate in this case, right? Here, you do have to use your calculator because, you know, you might not actually get the right answer by approximating. But let's see, 1/2, okay, times the constant, which is 2,000 newtons per meter. Okay, I'm not going to write the units because, you know, there's no point. In the test, I mean, if you want to do, okay, if you want to do a unit analysis, that's good, right? Because sometimes you might make a mistake and you might not realize what is going on. So writing down the units is probably useful. But because the questions are generally straightforward, it's just recommended that, you know, you just put in the values. And well, I mean, these equations are pretty simple, so you don't really need unit analysis. So this is 1/2 times 2,000 times 0.15 squared. Okay, so that's going to be, I mean, that's going to be about 22. Yeah, that's going to be 22.5, right? If you do the math, that's going to be 2,000 over 2 is 1,000, right? And then we have, if we convert this into a fraction, we have 15 over 100 squared, right? Okay, so 15 over 100 squared. Well, 15 squared is 225, right? So that's going to be 1,000 times 225 divided by 100 times 100, okay, which is basically 1 followed by 4 zeros, 10,000. 3 zeros go out, and we're left with 225 divided by 10, which is 22.5, which is pretty close to A. Okay, an elevator and counterweight are like Atwood's machine. An elevator mass equals 100 kilograms has a counterweight M equals 90 kilograms, connected by a cable over a massless pulley with no friction. The elevator falls starting from rest, a distance of 20.5 meters, and lands. What is the final kinetic energy of the system in joules just before the elevator lands? Okay, so let's draw our Atwood, our system over here. We have the pulley, and we have an elevator on this side, and we have the counterweight. Okay, we know the elevator is more massive than the counterweight, so the system will move in this direction. Okay, so this will be the positive direction, and so this will be the negative. Now, the mass of the elevator, big M, is 100 kilograms, and the little mass of the counterweight is 90 kilograms, which is just 10 kilograms less. Okay, now we know that the pulley is massless. Okay, there's no friction. That's good to know. The elevator falls at a distance, okay, a distance of 20.5 meters, and then it lands. Okay, it hits ground. So what is the final kinetic energy? Well, we need to know what's the final velocity, right, in order to know the final kinetic energy. So how do we do this? Well, I mean, this seems like a kinematics problem, right? But the problem is that we need to know what's the acceleration over here. Do we know what's the acceleration? It's not just 9.8, right? Because we have a system, we have an Atwood machine. So let's do Newton's second law. Let's draw a free body diagram for each. So the free body diagram for the big mass, okay, of the elevator, we have big mg going down, and we have the tension going up. For the little mass, we have, okay, we have the tension going up, right? And we have little mg going down. Now, if we solve this, okay, if we solve this system, if we use Newton's second law, the sum of the forces will be equal to, okay, big mg, okay, minus little mg, which equals to, okay, both masses, right? The sum of both masses, big M plus little m, multiplied by the acceleration. Now notice I skipped some steps, okay? So the tension cancels out because, well, tension is the same, right? Both tensions are the same since there's no friction and the pulley is massless. So we know that the acceleration in this case will be equal to, okay, the acceleration is going to be equal to big M minus little m multiplied by g divided by big M plus little m. Okay, so if you calculate it, you're going to get, let's see, this is going to be 100 minus 90 is 10. 10 times 9.8, right? 10 times 9.8. All of that divided by 190. Okay. So I approximated the value for acceleration, right, using g equals 10, and you're going to get 10 over 19. Okay, if you approximate it, just for approximation, right, purposes, meters per second squared. Now that we have our acceleration, right, we can use the kinematics equations, right, since the acceleration is constant. And we're looking for the final velocity, right? Given that this block travels a distance, vertical distance of 10.5, right, meters, then we can use a kinematics equation, which has, okay, acceleration, has distance covered, right, and velocity, but that doesn't have time because we don't know the time and we don't want to, you know, bother using time. So that sounds like the third kinematics equation, which says that final velocity squared equals to the square of the initial velocity plus 2 times the acceleration times the change in the distance. In this case, it's vertical distance, so it's delta y. Now we know that the initial velocity is 0, okay, since this starts from rest, right over here. So the final velocity is going to be the square root of 2 times a delta y. And if you use the approximation that I made, right, for g equals 10, we get that the square root of the velocity is the square root of 2 times 10 over 19, okay, times the change in distance, right, the displacement, which is 20.5. And if you do that, that's going to give you 2050 meters per second. And that's pretty darn close to, okay, 2000. So if you don't use the approximation, so if you actually use 9.8 like you should do, you're gonna get 2000. So, but you know, sometimes approximating is not a bad idea. Although in this case, it's irrelevant because you know, right over here, once you get to the radical, you're gonna have to use the calculator either way. So I guess just you know, to be safe, use g equals 9.8. Okay, a mass is revolving in a horizontal circle, meaning okay, it's facing downwards. So the circle is on the ground. So we're not worrying about gravity. The circle has a radius of 0.05 meters, and the mass has a linear speed of 0.63 meters per second. What's the period in seconds? We know that the period, okay, or well, the velocity is going to be equal to 2 times pi r, right? 2 pi r. Okay, so that's basically the circumference of a circle. Okay, the circumference, which is measured in meters per second. So that's going to be the period, t, in seconds. And the units work out, so that's meters per second. So that's basically the distance covered, okay, the distance covered. Okay, so that's basically 1 revolution per second per given, you know, unit of time. So we are given the radius, r. We're also given the speed. We're trying to find the period. So the period is equal to 2 pi r divided by the speed, which is 2 pi r. In this case, r is 0.05. All of that divided by 0.63. And so t is 0.5, okay, seconds, which is a. Okay. For question 8, I think I'm running low on battery. Okay. For question 8, a small ball is attached to one end of a rigid rod, okay, with negligible mass. The ball and the rod revolve in a horizontal circle, with the other end of the rod at the center. The path of the ball has a constant linear speed, and the force exerted by the rod is 0.5 newtons. The centripetal acceleration is 0.5 meters per second squared. What's the mass of the ball in kilograms? Okay, let me just see what's wrong with my battery. There you go. Okay. Now, let's see. So we know that we have something like this. So it's going to be horizontal circle, right? And there is a rod of negligible mass, and then there is a ball attached to the end of it. Okay, so we have a linear speed, right? It's constant, and we know that the force, okay, exerted by this rod is going to be 0.5 newtons. So it's basically the centripetal force, right? And we know that the centripetal acceleration AC is equal to 0.5 meters per second squared. And so we can use this to find the mass. Well, we know that the centripetal force is equal to the mass times the centripetal acceleration. We know both force and acceleration, so the mass equals to centripetal force over centripetal acceleration. And that's just going to be 0.5 over 0.5, which is 1 kilogram. That's a pretty easy problem. Okay, now for 9, a ball is revolving horizontally in a circle and is held by a rigid massless rod. The mass of the ball is 0.1 kilograms. The path of the ball has an angular velocity of 15 rads per second and a constant linear speed of 27 meters per second. What's the radius of the orbit in meters? So it's basically, okay, the same situation that we have over here. Okay, the only difference is the ball has mass of 0.1 kilograms. And the path, okay, over here has a angular velocity well, I shouldn't draw it like a line. It should be like this. The angular velocity omega equals to 15, okay, radians per second. All right, but we do know the linear speed, so v equals to 27 meters per second. And we know the relationship between the angular velocity and the linear velocity, okay? We know that the linear velocity is equal to the radius, okay, of rotation from the center of rotation times the angular velocity, omega, okay? So we're looking for the radius. So the radius is going to be the velocity over omega, which is going to be 27 divided by 15, and that's 1.8. 1.8 meters. Now, for question 10, we have a car goes around a curve and then around another curve. The parameters are the following. For the first curve, a force of F1 with radius r and speed v. So let's draw the first curve. Okay, right over here. We know the radius is r, the speed is v, and the force, okay, is F1. Now the second curve, okay, has force F2 and radius 6r. So this is 6r, and the force is F2. And the speed, okay, is going to be 3v. What's the ratio of the centripetal forces, F1 over F2? Well, pretty simple. First we have F1. It's going to be mass times AC1. And that's going to be, okay, the mass times v squared over r, right? So v squared divided by r, the radius of the first curve. For F2 we have m and then AC2, right? But in this case we have a velocity of 3v squared, right, divided by 6r. That's going to give us m 9v squared divided by 6r, and that's essentially, okay, F2 equals to 3mv squared divided by 2r. Now we define the ratio, okay, if we find the ratio F1 over F2, so F1 over F2 equals to mv squared over r, okay, divided by 3mv squared over 2r. The r's cancel, the m's cancel, the v's cancel. 1 over 3 halves is basically 2/3, which means that's going to be 0.66 repeating, and we approximate it to two significant figures. Okay, that's going to be 0.67. A person is on a circular carnival ride, or a Ferris wheel, that goes up and down with an axis of rotation parallel to the ground. It makes her feel twice her normal weight at the bottom and weightless at the top. Her centripetal acceleration is constant. What is its value in meters per second? Well, the second fact is already giving us the answer. We have a Ferris wheel over here, and if we think about what's going on at the top, right? That's the cabin, right? And at the top, we're told that the Ferris wheel makes her, okay, feel weightless at this point, meaning that the normal force equals to the force of gravity, right? So what's happening here is that the force, okay, the force of gravity equals to the normal force. All right, and that's going to be equal to the the net force, which is going to be centripetal force, MAC, and we're trying to look for the centripetal acceleration. So we know that Fg is basically mg, and that's going to be equal to MAC. The m's cancel, and we know that the centripetal acceleration is just the value of g, and that's E. Now for this question, question 12, a toy train of mass of 0.6 kilograms moves at 20 meters per second along a straight track. So we have a little train, okay, little train, and then the mass of the train is 0.6 kilograms, and it moves at 20 meters per second. Okay, now it bumps into another train which is much bigger. Okay, and the mass is 1.5 kilograms, and so it is also moving in the same direction at some speed. We don't know what it is. Now they stick together and continue on the track at a speed of 12 meters per second. What's the speed in meters per second of the second car just before the collision? So basically, what's V? Okay, we know the initial speed for the first train, and we know the final speed for both, because they're going to stick together. Then we have to use conservation of momentum in this way. So we're going to say that, okay, M1 V1 plus M2 V2, okay, so let's call this V2 over here. This is V2 equals to M1 plus M2 multiplied by V final. We're trying to look for V2, right? So we have that V2 equals to M1 plus M2 times V final minus M1 V1 divided by M2. If you substitute all your values in there, you're going to get the answer is 8.8 meters per second. Okay? So the most important part over here to remember is that when they say that two objects will stick together, that means that the final velocity, right? So what happens after is that the final velocity will be the same for both masses. So you just factor that out and you get the first mass plus second mass times final velocity. Okay, so that's 8.8 meters per second. A small ball is rotating in a circular horizontal path. The ball is held by a rigid massless rod. Its angular rate of rotation is 4 rads per second. Okay, so that means that the angular velocity omega is 4 radians per second. The kinetic energy of the ball is 19.2 joules. So what is the moment of inertia of the ball with respect to the axis of rotation? Okay, so for this question, we know that the kinetic energy, for rotation, right, is going to be 1/2, okay, I, which is the moment of inertia, times the angular speed squared, and that's analogous. That's analogous to 1/2, okay, mv squared, where m is mass and v is velocity. In this case, I is basically the analogous of mass, so it's basically a resistance. It's a resistance in motion. That's what inertia means. And the angular velocity is just the analogy of, okay, it's analogous to velocity, linear velocity. All right. What's the moment of inertia of the ball with respect to the axis of rotation? Well, we just solve for I. So I equals to 2 times the kinetic energy divided by the square of the velocity, angular velocity. That's going to be 2 times 19.2 divided by 4 squared. That's going to get you to 2.4. 2.4 kilograms meters squared. A small ball is rotating in a horizontal path on a massless rigid wire around a vertical post. The radius of the ball's orbit is 1.2 meters, and the moment of inertia of the center of mass of the ball about the axis of rotation is 8.6 kilogram meter squared. what is the ball's mass in kilograms? Okay, so we're going to consider this ball because it is small, right? It is a small ball. We're going to consider it a point mass, right? So the moment of inertia for a point mass, okay, is just going to be the mass times the square of the radius. All right. Now, we're trying to look for the moment of inertia, for the mass, right? We know what's the moment of inertia, and we also know the radius. So all we have to do is solve for m, right? That's going to be I over r squared, which will be 8.6, divided by 1.2 squared, and that'll give you 6. Okay, 6 kilograms. All right. So let's move on to question 15. 3 particles with M1 equals 2 kilograms, M2 equals 3 kilograms, and M3 equals 5 kilograms are located respectively at R1 equals I hat plus 2j hat, R2 equals I hat plus 3j hat, and R3 equals 2 I hat minus 2j hat. So find the location of the center of mass in meters. Now, we know that the location for the center of mass will be equal to the sum, okay, the sum of all your mass times radius, right? Mass times the distance, okay? Mass times the location, divided by the sum of all your masses. So basically, mr divided by the sum of all mr's divided by the total mass. So we have something like this. For the first one, so for m1, we have, okay, m1, and then we have times, actually let's just input the values already, okay? So we have m1, which is 2, and then times r1, right, which will be I hat plus 2j hat, okay? And then plus m2, which is 3, times r2, which is going to be I hat plus 3j hat, and then plus 5 times 2 I hat minus 2j hat, okay? All of that's going to be divided by the total mass, which is 5 plus 3, which is 8 plus 2, which is 10, okay? So we just do these operations over here. 2 times I is 2i, plus 3i is 5i, plus 5 times 2 is 10, 10 plus 5 is 15. So we have that the location for the center of mass is 15, okay, I hat. And then we have plus 2j hat, right? Times 2 is 4j hat. 3 times 3 is 9. 9 plus 4 is 13j hat. Plus 5 times negative 2 is negative 10. So 13 minus 10 is 3. So 3j hat. All of that divided by 10. And that's going to be 1.5 I hat plus 0.3 j hat. That will be the location of the center of mass. And all of this is in meters, of course. Now, question 16. We have a mass of 1 kilogram pulls down vertically on a string that winds around a solid cylindrical rod attached to a disc. That's important. The rod is inside the disc, right? This is the rod that we're talking about. We're not talking about this. This is the mass, right? This is the weight that's pulling down the cord. Now, the cylindrical rod, okay, is attached to the disc, and then both of them, okay, the disc and the rod. So this and this over here, the rod and the disc together have a combined moment of inertia of 10 kilograms meter squared. So that's important to keep in mind, right? Because it might be confusing at first. the rod has a radius of 0.1 meters and the disk has a radius of 1 meter. And the system is initially at rest. Okay, what's the angular acceleration of the disk? So for this one, what we're going to do, okay, is we're going to do the sum of the torques. But first, okay, so for that we're going to have to find the sum of the torques equals to, okay, in this case, the only one force that's acting on this is the force of tension over here. Okay, and if we do a free body diagram for this, we know that tension is equal to mg, right? So the mass that's pulling this down times the gravity. So we can say that it's going to be mg times the radius r, right? So F times F cross r, the radius of the disk, right? We're looking for the radius of the disk. And then that's equal to the moment of inertia times the angular acceleration, I alpha. And we're looking for, okay, the angular acceleration. So we solve for alpha. And alpha is mg times the radius divided by the moment of inertia. Now, we're going to be careful here because the torque is acting, okay, on the rod. And the radius of the rod is 0.1 meters, not 1. Right? 1 meter is the radius of the disk. But because this torque is acting on the rod specifically, which is making the whole thing rotate, right? The disk and the rod together. We're only looking for the radius of the rod. So we substitute the values, and we have that the mass, okay, the mass of the original, this weight is going to be 1 kilogram times 9.8 meters per second squared times the radius of the rod, which is 0.1. All of that divided by the moment of inertia, which is 10. 9.8 times 0.1 is 0.98, and divided by 10 is 0.098. That's going to be the angular acceleration, okay, in radians per second squared. A disk with mass m and radius r rolls down a 10-meter long incline starting from rest. So we got something like this, and we got this disk, okay? It's got a radius of r, and it falls down. Now the distance from here to here is 10 meters. Now initial velocity is 0, v0 is 0, and the incline makes 30 degrees with the horizontal. So we got theta equals to 30 degrees. So find its speed in meters per second at the bottom of the incline. We want to find the speed of the disk at the bottom. Now, here's the thing. There is a reason for why they don't really give us the values for m and r, right? We don't really need them. Now, we have to assume that, okay, the disk is rolling down the incline without slipping, right? Because otherwise, there will be an issue there, right? And we're trying to use the easiest method in order to solve this problem, because in the test you don't want to get stuck on a problem for too long. So for this specific problem, we're going to use the fact that we have an initial speed, which is 0. We also have, okay, some difference, some height from here. We have a height with respect to the bottom, and that tells us that we have potential energy. So all of these things suggest us to use conservation of energy. So let's lay out the law of conservation of energy equation. We know that the initial energy will be only gravitational potential energy, UG, and the final energy will be kinetic energy, right? because it will just be moving and rotating here. So it will be moving linearly, but it will also be moving, it will be rotating. So that means that the total kinetic energy, right? The total kinetic energy, so kinetic energy total is going to be equal to the linear kinetic energy plus the rotational kinetic energy. And we know that linear kinetic energy is 1/2 mv squared, right? So let's do UG8. UG is mg times the height. Linear kinetic energy is 1/2 mv squared, and rotational kinetic energy is 1/2 I, the moment of inertia. I times the rotational, the angular velocity squared. Now, we want to solve for the final velocity. So we have to change this over here. We know that this is a disk, right? So that means that the moment of inertia of a disk, from your formula sheet, will be the mass times the radius squared divided by 2. So we can use that to put it in the conservation of energy equation and solve for V. And we're also going to use the fact that the angular velocity is the linear velocity divided by the radius. So we have that mg times the height equals to 1/2 mv squared plus 1/2 times the moment of inertia, which is mr squared over 2, and then times the angular velocity squared, which is v squared over r squared. And look at that, the r's canceled, so the radius of this disk doesn't matter. It could be extremely huge, it could be extremely small, it does not matter. Okay. Now the mass doesn't matter either, because as you can see, it just cancels out, right? If you divide by the mass on all sides, that cancels out. So you're left with the following. You're left with GH equals to v squared over 2 plus v squared over 4. If you solve for v, we find the common denominator, so multiply by 2 over here, top and bottom, and you get 2 plus 3, 2 plus 1 is 3, so it's 3/4 v squared. So that means that v squared equals 4/3 GH. And so your v will be equal to the square root of 4/3 GH. But what's h? We need to find h, the height. It's not 10 meters. 10 meters is the distance, along this incline. So we have to use some trigonometry. If this is your height h, and we know that the angle is 30 degrees, then we can say that, sine of 30 degrees is equal to opposite over the hypotenuse, right? The opposite is the height. The hypotenuse is 10. So h equals to 10 sine 30. And sine 30 is 1/2, so h is 5 meters. So the velocity will be equal to the square root of 4/3 times 9.8, times 5. And that's approximately 8 meters per second. Okay, for this question, a disk like a yo-yo starts from rest and falls down from the position shown in the figure. Unwinding the light cord, the mass of the disk is m equals 26.7 kilograms. Its radius is r equals 0.10 meters. And so what is the initial angular acceleration alpha of the disk in radians per second squared? Okay, this is a pretty fun problem. So here, this is a little tricky, but we have to take advantage of something here. We have to use Newton's second law. So what's going to happen here is, believe it or not, tension, okay, the tension over here, the magnitude of the tension is proportional to the force, okay, the gravitational force, mg. Even though it's not like, it's not acting at the center of mass, right? We're going to, okay, use Newton's second law in such a way that we include tension in the equation. So we say that the sum of the forces is going to be equal to, now this is going to be the positive direction of the acceleration, the angular acceleration, right? Because, if you think about it, it's going to move counterclockwise. And because tension goes, okay, it points towards the positive direction of rotation, tension will be, in fact, okay, positive if we were to use, okay, the sum of the torques. But for linear, okay, acceleration, we have something like this. It's moving down. So we have to say tension is negative and mg is positive. So mg minus the tension equals to m times linear acceleration. Okay, very nice. Now let's find the sum of the torques, right? Because we need to find something in terms of m and a and g instead of just t. We don't want t. T is annoying. So we have to find the sum of the torques. Sum of the torques is equal to, in this case, we said that tension goes along the direction, okay, the positive direction of rotation. So that's going to be the torque times the radius, okay, of this disk, which will be equal to the moment of inertia times angular acceleration, I alpha. Okay, so tension is equal to I alpha divided by r. And we know that because this is a disk, the moment of inertia is mr squared divided by r. I'm sorry, mr squared divided by 2. Okay, times alpha, and then divided by r, right? Let me see what's the battery that's left. Oh, 6%. Crap, I only have 2 questions left. Okay, so let's finish this and then I'll have to charge this computer. The r cancels out, and we have that tension is equal to the mass alpha times r divided by 2. We substitute that in our original equation, okay? And we also know that alpha is equal to the linear acceleration divided by r. So look at that. Tension is m alpha over r times r over 2. R's cancel out, so we have m alpha over 2. We go back to our original equation and we have that mg, okay, minus m alpha, I'm sorry, ma. We're talking about angular acceleration now. I mean linear acceleration divided by 2 equals to ma. 1/2 plus 1 is 3/2. So that means that we have 3/2 ma equals to mg. And so the m's cancel. So the acceleration, okay, the acceleration will be 2/3. 2/3 of g. Okay. But we're looking for the angular, I'm sorry. So just divide by r, and then you're gonna get okay, 65 radians per second squared.